Today we are going to work, which is going to be quadratics and some higher degree polynomials. And the first thing we're going to cover is graphing quadratics in different ways. So a lot of everything we've done in class, as we've covered, all the operations that we need to solve these quadratics we've already done. We're just going to put it in the context of graphing a quadratic. So on this INB, you have 3 graphs that we're going to work with. And if you just glue one on the left side, one on the right, then when we're done graphing, we'll use the graphs on the other page to graph the quadratics. So here's our first form, which is called vertex form. And this should be familiar because we just got done shifting functions. So this is like our shifting form right here. And it kind of makes complete sense. If this is a quadratic, A would be our vertical stretch, H would be our left to right movement, and K would be our vertical up and down movement. So it makes sense that our vertex would be located, well, it got shifted H units to the right and K units up. How it opens, whether it opens up or down, depends if A is negative. That's our x-axis reflection. So if A is greater than 0, then it's going to open up. And if A is less than 0, or if it's negative, the parabola will be opening down. Remember, a parabola has a symmetric across the y-axis, but if it shifts, it's still symmetric across its vertex along the vertical line of the axis of symmetry, which is x equals whatever the x value of the vertex is, so x equals h. Okay, when we graph a quadratic equation, what we want to do is we want to find a couple key points. Our first one is our vertex, and this one is very easy to find, most friendly one. Find the vertex. And so this quadratic, which used to be x squared, got shifted. That 0, 0 point got shifted left 4, which is the vertex, and down 3. And so that's where our vertex is now located. So we know a quadratic, right, is also going to open up or down depending on if our A or our vertical stretch or compress is a negative or a positive. So this one is a positive 1. So this opens up. So we know right now, we know 1, 2, 3, 4, negative 2, 3. We know my quadratic opens up something like this. We just don't know the x-intercepts. We know it's going to have x-intercepts because our vertex falls below the x-axis and it opens up. So after we find our x-intercepts, we will be done. So I'm going to write x-intercepts. And the easiest way to solve for our x-intercepts is take a quadratic equation, and we're going to set it equal to 0. That's where our y values are 0. And then we're going to solve this one. We're going to use the square root method because I only have one visible x. I can isolate it. Just remember, these are quadratic equations, so I'm going to have 2 solutions. Remember, the fundamental theorem of algebra says whatever the degree of the polynomial is how many solutions your polynomial will have, whether they're real or complex. So I'm going to square root both sides. And I get plus or minus the square root of 3. That indicates my 2 x-intercepts. And there are my 2 x-intercepts. Now remember, before we just left it in radical form, but since I'm going to graph this, it makes sense that I'm going to need some decimal approximation, so I have an idea. I don't know really where negative 4 plus the square root of 3 is, so I'm going to go to my calculator, and I'm going to put in 4 plus the square root of 3, and I get 5.7. Oh, it was negative 4. And I get negative 2.3. And then I'm going to go back and do -4 minus the square root of 3. And I get -5.7. No reason to take your decimal out any further than that. I can't. I'm using these numbers as approximation to graph. I can't graph really any better than a tenth, and a tenth is pretty hard to do. So what I'm going to do is I'm going to put all this information now onto my graph. So I know I go -4, -3, and let's just verify my x-intercepts. I have -2.3 and -5.7. So -2.3 and 5.7. My axis of symmetry is the vertical line that splits my parabola right in half, and that definitely looks like my x-intercepts are halfway, symmetric across that line. Another way you can graph some points if you don't have x-intercepts is the property of a quadratic. When I'm one away from the vertex, if I square that, I'm at 1. So on both sides, so left 1, square it, go up 1. If I go 2 away from the vertex, then I'm 2 units. And if I square that, then I'm at 4. So I'm going to go 2 to the right and then up 4. 1, 2, 3, 4. To the left, 1, 2, 3, 4. That's an easy way to get some additional points. Now that is if your A is a 1. Now obviously if your A was like vertically stretched, then when I went over 2, I would go up 8. I would multiply that by the magnitude. And same thing with a compress. We'll see that as we go forward. Okay, and I didn't put the axis of symmetry on there, and that is x equals -4. Remember the x-axis, the x value of the vertex. Now, standard form is a little bit harder. We're going to first learn by completing the square. So there's 2 ways we're going to learn in standard form. And my vertex is still going to be h comma k. And my opening is still going to be the same. Right, and when we're talking about the A, we're still talking about that A right there. Okay, it doesn't matter what form it's in. And then my axis symmetry is x equals h. And notice on this method, I definitely want to be completing the square. Okay. Now, when we complete the square on this one, we're going to do it slightly different. So you might want to pay attention. It's a little bit different than how we were doing it when we were just solving. Because I'm not going to be solving this necessarily right away. I'm going to be converting it using the completing of square into vertex form. Okay, so I'm going to go from 2 to 1. So remember, the whole thing about completing the square is my A value. Well, let's just start here. I'm going to create a new constant term that's going to cause, right, this trinomial to be a perfect square trinomial. So I can write it like if we look over at number 1, right? So I can write it as this part, right? X plus 4 squared. Okay, so back to my problem, and I can't get rid of any number, so I still got that plus 1, but notice I'm not putting it on the other side of the equal sign because I'm not solving it. So I haven't set f of x equal to 0 yet for the x-intercept. Now, before I can complete the square, my squared term's coefficient is -1. That has to be a positive 1, no matter what. It has to be. I have to factor out my x squared, the coefficient, if it's not already just a positive 1, which it's not. It's a -1, so it's got to factor out. Okay, so that's my next step. And that's what's different than the time before, was that we just divided everything by the -1. This time we're going to hold it because that's actually our reflection, right? So we don't want it to go away by dividing it out. So I'm going to factor it out so it remains. And all that's going to do is change the sign of those first two. Now notice I'm going to keep the constant term of 1 outside of that factor, okay? And I'm going to add a blank. Okay. The next thing that we're going to do is we are going to complete the square. So half of the middle term, so half of 4 is 2, and then I square it, which I get a 4. And then when I factor that, I get x plus 2 squared. Now, here's the tricky part. Before, what I added to the right side, or to the left side, I added to the right side of the equal sign. Because that's how you balance an equation on different sides of the equation when I completed the square before. However, this time when I complete the square, I'm on the same side of the equation. So if you notice, when I am adding this 4 over here, the only way to balance the equation out on the same side is to subtract that value, right? So if I add a 4, if I subtract 4 on the same side of the equation, I haven't added anything. I've added 0. So that's what I want to do to balance out the equation when I complete the square to get it in vertex 4. However, another tricky part is I did factor out this -1. So if we use this distributive property, notice I would distribute this -1 back in and get -x squared minus 4x minus 4. So I'm not technically adding a 4, I'm adding a -4. So what I have to add to this is a +4 on the other blank to cancel out for that -4 that I put in that blank. Now, the -1 is also factored out, but so if you have to factor out in the beginning, you have to be careful about what number you're going to put in your blank over here, because you've got to pay attention to know that what that number I factored out is going to cause my number in the parenthesis that I add to change. Okay, and so then that's how I get a 5. So now I'm in vertex form. Okay, so I'm ready to talk about all of my stuff. So my vertex is going to be -2, 5. My axis of symmetry, well, that's going to be x equals -2. This thing's going to open down because my a was -1. And then I need to find my x-intercept. So now this is where I want to set my equation equal to 0, and I want to solve. And I'm going to divide by -1, and then I'm going to square root, and I get x plus 2 is equal to plus or minus square root of 5, and I'm going to finish that off with x is equal to -2 plus or minus the square root of 5. And now I need to go to my calculator and get to approximations. Okay, so I'm going to do -2 plus the square root of 5, and I get 0.2. And then I'm going to do -2 minus the square root of 5, and I get -4.2. So 0.2 and -4.2. Let me just double check that. Okay, and now I'm ready to graph this. So I have my vertex at -2, 5, and I had a 0.2 and a -4.2, axis of symmetry, and there we go. Now, again, if I wanted to get some better points, I could go 1 away from my vertex, and I'm going to go the distance of 1. This time I would have to multiply by -1 because my a is -1. So that gets me to down. If I went 2 away, I'd go 4. 1, 2, 3, 4. 2 away. 1, 2, 4. And that also gets my y-intercept. And I have my graph. Okay. Now my next is standard form, where I'm going to use the axis of symmetry to be able to get the graph. So notice on all of these, my axis of symmetry goes through my vertex. So if I know the axis of symmetry ahead of time, then what I know is the x value of my vertex, right? So there is an equation for a vertex that you can find it every time. and it is x equals opposite b over 2a. If you remember from the quadratic formula, it's a part of it. And my a opens the same up here and down here. My axis is symmetric. Oh, why'd I put that? So there's the equation to the axis of symmetry. And so my vertex is the axis of symmetry. That gets me the x value. Now, if I want to know what the y value is, well, once I know the x value, I plug that x value back into the quadratic equation to find the y value, right? So on this one, instead of converting it into vertex form, I'm just going to go after the vertex. And I'm going to do that by locating my a, my b, just like the quadratic formula. No, I don't need my c. I'm going to write it down. So here's my x value. Here's my axis of symmetry, or the x value of my vertex, which is opposite b, 2 times my a value, which was 1, which I get 4. So now I know my vertex has the x value of 4. Also know my axis of symmetry is x equals 4. Now, if I want to find the corresponding y value to my vertex, well, that's pretty easy. I'm going to go ahead and I'm going to plug that back in to the equation and say if I input 4, which is the vertex, what is the y value? And then I obtain the vertex. So I get 16, 8 times 4 is minus 32, plus 16, and those all cancel out. I get 32 minus 32 is equal to 0. So it looks like my vertex is my x-intercept. Okay. So there's no reason to go ahead and solve this, but I'm going to solve for my x-intercepts anyway. So x squared minus 8x 16 equals 0. Always want to be able to factor in this scenario. If I can't factor, then I'm going to go to the quadratic formula. But this is x minus 4 times x minus 4. And remember, when you have a doubled up, when you have a perfect square, you know your x-intercept is also going to be your vertex, right? So I have these twice, called a double root. And so I know that's always going to cause my vertex to be the x-intercept. Okay, so this one opens up, and I'm ready to go graph this. Okay, so I'm going to go to 4. It opens up, and guess what I don't have? I don't have any other x-intercepts, and it's really hard to graph when you only have one point, a u-shaped function, to where it doesn't look awkward or different from what it's supposed to. So this is where that 1 away, up 1, 1 away, up 1, over 2, 1, 2, 3, 4, over 2, 1, 2, 3, 4. Just be careful. If your A is something than 1, then you're going to have to either stretch or compress that number. I'll put my axis of symmetry. That's that x equals 4 line. I'll do that on the one up here. Okay. Now the last is just a problem that you could run into on homework, and it's creating an equation of quadratic given information. So we want to write an equation so we know the vertex and we know a point, and we're going to use vertex form. So we're going to say y is equal to a times x minus h plus k, and we're going to plug all of our information in. So I know I have an x and a y and an h and an k, and I'm going to plug all that in. My y is 9. I don't know my a value. That's what I'm after. My x here is 0. My vertex x value, or the h, is negative 2. So it turns to plus 2. Oops, got my square. And then my k is a plus 5. Okay, so I'm going to simplify this. Obviously, I would do add inside. 0 plus 2 is 0. But then I'm going to square, and I get 4a plus 5. And then I'm going to solve. And this one I get in my a is a positive. Okay, so I'm ready to write my equation. I'm going to just put that positive 1 in there. Let's to show that I found it that way. And then if I wanted to graph that, I have that extra graph. So have fun doing your homework. See you on Thursday for your test, or Friday.